Okay, hey guys, we're going to start off this video lesson with a little bit of a domain review. So I would like you to go ahead and pause the video and you're going to solve for the domain of these three problems. This third one is going to be a little bit different from what you've solved thus far, but see what you can do with it. Go ahead and you can turn back to your notes and use them as a reference for finding the domain. What is the domain of these three functions? Okay, we're going to spend about 4 minutes going through these three, just as a reminder, because domain is going to come back at the end of this unit, and I want to make sure that we don't forget. So for this first one, the square root of x minus 3 plus x squared. When you're finding the domain, you want to figure out where your restriction in your function is and what that restriction is. So this square root of x minus 3 is my restriction. There's no restriction to my domain in x squared. I can always plug in any x value into the function x squared. Versus inside of my square root, this square root cannot be negative. However, in this equation it can equal 0. So I'm going to set my square root, or what's inside of my square root, x minus 3, so that it cannot be negative. Well, if I think about where my numbers are not negative, if they're not negative, then they are greater than 0. Greater than 0. So I want this number, whatever it is, to be positive or greater than 0. It can also equal 0, so I'm going to give it an equal to bar. Then I'm just going to solve this inequality. So I'm going to add 3 to both sides. X is greater than or equal to 3. So that means that on my number line, I can kind of ignore this one now. At 3, I'm going to have a closed circle, shading everything to the right. My inequality is going to go bracket 3 to infinity is my domain. Okay, let's take a look at this next one. 1 over 2x plus 5 plus an x cubed. Okay, where is my restriction in this domain, or in this function? Great, this 2x minus 5, I can never have a 0 in my denominator. So 1 over 2x plus 5, this cannot equal 0. So my denominator, 2x plus 5, cannot equal 0, and I'm going to kind of solve this unequation or anti-equation. So I'm going to subtract 5 from both sides. So I get 2x cannot equal a negative 5. Divide by 2. And I'll get that x cannot equal negative 5 over 2. Well, if I graph this on a number line, here's negative 5 over 2. If it cannot equal negative 5 over 2, I'm going to put an open circle. However, x can equal anything else, just not this one value. So I'm going to shade to the right and to the left. When I write this in interval notation, my solutions are going to start at negative infinity and go to this solution, negative 5 over 2. Since it's an open circle, it's going to get a parentheses, union, and then they start up again at negative 5 over 2. And they go to infinity. So that would be my interval notation. Okay, let's look at this third one. Like I said, this was kind of the one that had some combinations that we hadn't talked about. So I've got a couple different restrictions in this equation. The first one is my denominator in this fraction. So the square root of x minus 5 cannot equal 0. And what's inside of that square root. So x minus 5 also has to be positive. It has to be greater than 0. Since this cannot equal 0, I'm going to make sure that I don't set this to be or equal to 0. If this were not in my denominator like it is in problem number 1, that's when I can put my equal to bar. I can set it or equal to 0. But in this problem, since it's in the denominator of a fraction, now what's inside of my square root actually cannot equal 0. So x minus 5 cannot equal 0. but it has to be positive, so it has to be greater than 0. So this equation tells me a little bit more about the function. It uses the cannot equal 0, and it tells me greater than 0. So I'm only going to solve this second inequality. I'm going to add 5 to both sides. So x has to be greater than 5. If I look at the second equation, so I've got a second restriction to my domain. I've got another square root, x minus 3. Remember, this has to be positive, so it has to be greater than 0. But in this case, this function is not in a denominator. It's outside of a denominator, so it actually can equal 0. I can have something plus 0, that's fine. So if I solve this inequality, add 3 to both sides, x has to be greater than or equal to 3. So I need to graph this in such a way so that both of these things stay true. So if I've got 3 and 5 on my number line, well, x is greater than 5. I'm going to put an open circle at 5 and shade to the right. X is greater than 3. Well, I can't put a circle at 3 because then I wouldn't be solving this inequality. So actually, I'm going to ignore this inequality, x is greater than 3, because my x is greater than 5 eventually jumps up with it. If I were to graph my x is greater than 3 inequality, it would look something like this, where eventually at 5 it would start up and my solutions would overlap. So I only can look at where my solutions overlap, and in this case, an open circle overrides any closed circles. So that is just this piece of my inequality. So my domain for this function is going to be parentheses 5, comma, infinity. Just a little review of domain. We'll keep talking about it again, so if you're confused with this last problem, don't worry. You're going to have some time to review it again before the unit test in a couple of weeks. Okay, the bulk of this lesson is going to be about graphing polynomial equations. So to start off this lesson in graphing polynomial equations, we're going to start off by talking about finding the roots of an equation. So as a reminder, and I know you guys talked about this last year in Algebra 2 and 2 years ago in Algebra 1, when you're finding the root of a function, there are lots of words that we use for the roots. Roots can be called zeros, they can be called solutions. So when you're finding the root of a function, really what you're doing is you're setting that function equal to 0. So if I'm finding the roots of these 3 equations, I'm going to set each of these equations equal to 0. I'm going to pause here and just say that if you are not currently taking notes with your notebook out, you should pause and take that out so that you've got these notes to reference later, not just the video to reference. Okay, so if I'm solving this equation, x squared minus 4x equals 0. X squared minus 4x equals 0. Well, I've got a quadratic on one side, 0 on the other. When this happens, in order to solve and figure out what x can equal, I am going to factor. First, I want to see if there are any greatest common factors. So do these 2 terms have something in common? And the answer to that is yes. I can pull out an x. That x isn't just going to disappear. I'm going to leave it on the outside. When I pull out the x, I'll be left with x minus 4 is equal to 0. You may remember from the last unit, but when I'm finding solutions, once I've factored it out, I'm going to set each piece equal to 0. So one solution will just be x equals 0. And that's what happens when I factor out an x from my terms. The second solution, x minus 4 is equal to 0. I'm going to add 4 to both sides so that I get x is equal to 4. And these would be the 2 roots of my equation. go ahead and solve this one. You're going to be factoring it out. You may want to use Snowflake in order to help you do so. Factoring this out, you're finding two numbers that multiply to 8 and add to a -9. That's going to be -1 and -8. I'm going to set these as binomials. So 1x minus 1 and 1x minus 8. And I'm going to set those individual pieces equal to 0 so that I get the roots 1 and 8. Okay, the third kind of scenario that you might come across is when the equation is already factored out for you. So I give you something like h of x is equal to x times x minus 1 times x minus 2. And that makes it so easy. You just set each of those pieces equal to 0 just like you would if you factored it yourself. So this will give me 3 roots. One of them is easy, x equals 0. Done. The next one I've got x minus 1 is equal to 0. If I add 1, I'll get x equals 1 as my second root. Third root, take my third piece, x minus 2 is equal to 0. Add 2 to both sides and I'll get x equals 2. Okay, so that's just in general how to find roots of different types of scenarios you might come across. One with a greatest common factor you have to pull out, one with Snowflake, and then the third where it's already factored out for you. Like I said at the beginning of this video, we're going to be talking today about how to graph polynomial functions and polynomial equations. Before we get into the graphing piece, I want to organize some thoughts about end behavior of the polynomials. So you're going to go ahead and in your notes, you're going to set up a table that looks like this. Name, polynomial, basic sketch. Go ahead and pause to set up. Okay, so if I've got a linear polynomial, my function, let's name it f of x, is going to look like just x. I could have an x plus 2, or f of x equals x minus 3, or I'll give a couple of examples, f of x equals just an x, where I'm adding or subtracting some value. But there isn't another x in my equation. This is what my function will look like. Well, I know that a linear equation just looks like a line. So that's going to be my basic sketch. We're focusing on the end behavior of this line. So on the left hand side of my line, the arrow is going downwards. On the left-hand side, the arrow is going downwards, versus on the right-hand side, my arrow is going up. Look at our next one. So a quadratic equation, my general form of that is going to be g of x is equal to x squared. But a quadratic equation can have other things going on with it too. This could also be h of x is equal to x squared plus x. My highest power is a 2. Which makes this a quadratic equation. So I could also have something like L of x is equal to x squared minus 9. And this would also be considered a quadratic equation. We know from our parent functions that our basic sketch of a quadratic equation looks like a parabola. If I focus on the end behavior of my parabola, so on the left side, my arrow is going up. Left, I'm going up. On the right side of my parabola, my arrow is also going up. So on the right side, I'm also going up. Okay, with our cubic equation, so this could be something like f of x is equal to x cubed. It could also be something like g of x is equal to x cubed plus x squared plus x minus 1. So I can have a bunch of other stuff going on. As long as my highest power is 3, I know that I've got a cubic equation. My parent function will be this x to the power of 3. All of our cubic equations, we know, have the same kind of form, where if I look at my end behavior, the left arrow is going down, and our right arrow is going up. Left arrow going down, right arrow going down, up. Okay, we've got two more, and at this point you might start to kind of recognize a pattern, maybe not yet. If I've got x to the fourth, so this would look like the function f of x is equal to x to the fourth power, or it could be something like r of x is equal to x to the fourth plus 5x cubed minus x squared plus 2. This would also follow the same form. In this case, my function is going to look something like this, where if I look at my end behavior on the left-hand side of my function, my arrow is going up. And on the right-hand side, my end behavior is also going up. Okay. Start to see if you can recognize a pattern between my end behavior and my polynomial. What do you think the end behavior for an x to the fifth is going to look like? Okay, let's see if your prediction was correct. If I've got f of x equals x to the fifth, or if I've got s of x is equal to x to the fifth plus 4x squared plus x cubed minus 3 or 2, whatever. This function is going to look something like this. It might have a little bump in between, but my end behavior model, the left end is going down, my right end is facing up. Okay, so to summarize my end behavior, if you have an even power, if your largest power is even, like x squared or x to the fourth, both ends of your function face up if you have an even power. Largest power is odd, then the left end goes down, the right end goes up. Your ends are going in opposite directions. Opposite directions. So with this function, if your largest power is even, both of your ends are facing up. Maybe some weird stuff is happening in between those ends, but in the end you know that your ends both face up, versus with your odd power, right end faces up, left end faces down. And again, there might be some weird bumps or curves in between, but you know your general end behavior. Okay, so now we're going to talk about graphing polynomial functions, and there are a couple of steps that you want to take or steps that you want to consider. So if I am trying to graph the function f of x equals x times x minus 6 times x plus 7, your step one is to determine the end behavior. So in order to do this, I have to consider what the highest power of this function is going to be. One easy way to do this is to imagine, okay, if I multiplied all of these things together, what will my highest power end up being? So if I multiply x minus 6 times x plus 7, my highest power is going to be this x times x, so x squared. And then if I multiply that x squared by my x squared times x, that's going to give me an x to the third. And that is going to be the largest power that I can get by multiplying these three things together. So in this case, my highest power is going to be 3. Since my highest power is odd, my ends are going to go in opposite directions. Right end up, left end down. Okay, step number 2 is to find my roots. So this is a nice function that's already been factored out for me. I'm going to set each piece equal to 0. So the first piece, x is equal to 0. Second piece is my x minus 6 is equal to 0. If I add 6, well, x will equal a positive 6. My third piece is x plus 7 is equal to 0. If I solve for x, subtract 7 from both sides, I'll get x is equal to negative 7. Okay, when I've got a root, and I didn't mention this before, you find your x values. In a root, your y value always equals 0. Your y value always equals 0. So if I were to write these as coordinates, I've got an x and a y value. This would be x is 0, y is 0. This would be the point, x is 6, y is 0. And this will be the point, x is negative 7, y is 0. Okay, so my last step is to sketch my graph, to put these two ideas together. So first I'm going to plot my 3 zeros. So I've got 1 at 0, 0, 1 at 6, 0, so I'm going to go 1, 2, 3, 4, 5, 6, nowhere along the y-axis, and 1 at negative 7, 0, so 1, 2, 3, 4, 5, 6, 7. Okay, so those are my 3 roots. Go ahead and graph them on your graph. Now I'm going to set up my end behavior. So my ends are going to come from the last roots on either side. So the rightmost root, my end goes up. The leftmost root, my end goes down. And now I'm going to connect my roots. I've got to kind of follow the curve of the line. So this end is going up and through. Well, but now I've got to come back down and I've got to touch this root. So I've got to go back down through 0. Now my line is going down, and I've got to go back up. So I'm just going through each of these roots to connect my end behavior. So this is what my general graph of this function will be. You only need the critical points of your roots. I do not need to know how high or how low your graph is. Okay, let's take a look at this next function. F of x equals x minus 5 times x minus 6 times x plus 7 times x minus 2. What is the highest power going to be when I multiply these 4 roots together? Okay, hopefully you said x to the 4th. So if I multiply x times x, I've got x squared, times another x, I've got x cubed, times another x, I've got x to the 4th. That's going to be my largest power. Now I've got to go ahead and find my roots. I want you to find the coordinates for your 4 roots based on these 4 different factors. Go ahead and find those coordinates. Okay, go ahead and check your work for each of these 4 points. You should end up with the points 5, 0, 6, 0, negative 7, 0, and 2, 0. So our next step, you're going to set up your coordinate plane, and we're going to plot these 4 points. So negative 7, 0, I'm going to go to the left, 1, 2, 3, 4, 5, 6, 7. Nowhere along my x-axis. 2, 0, I'm going to go to the right 2. 5, 0, I'm going to go to the right 5, 1, 2, 3, 4, 5. And 6, 0, 1 more. Okay, if I consider my highest power, what are my ends going to be doing in this function? Correct, they're both going to be facing up. So at my 2 ends, I'm going to put ends that are facing up. And then from here, I'm just going to follow the curve of the line. So I'm going down, I have to go back up to get through this point, cross over, go back down to get through this 0, and then I've got to go back down and cross back up. So my function graph should look something like this. We are going to pick up with this on Thursday, but make sure that you come in with questions about this video if things are unclear, so that you can get clarification while you're working on your problem set. And that's it.